So after explaining the whole Millikan experiment, do you finally understand what the photoelectric effect is and means?
Yeah, man, I think I understand it pretty well now. But it'd be pretty rad if I could see it in person.
Is it me, or are you just like looking different every time I look at you?
No, I don't think so.
Okay, well, here's the quantum source. Take it away.
The microwaves will excite the electrons in this metal and cause them to eject.
Sorcery!
And now for the physical applications of the photoelectric effect.
Of the photoelectric effect. Some of the most important are photomultipliers, photodiodes, and photovoltaic cells. A photomultiplier consists of a source of primary photoelectrons, a photocathode, and consecutive secondary electron emitters known as diodes. Each subsequent emitter is supplied with high electrical potential in comparison with the preceding one. Photoelectrons produced by the photocathode are accelerated to the first emitter, ejecting secondary electrons from its surface. The latter are then accelerated to the next emitter, knocking out even more electrons. The procedure is repeated an arbitrary number of times, resulting in a detectable current from a very low source of incident radiation. Photodiodes operate by absorption of photons or charged particles and generate a flow of current in an external circuit that is proportional to the incident power. Of particular interest are semiconductor photodiodes. These devices are p-n junction diodes that can be formed by diffusing either a p-type impurity anode, such as boron, or an n-type impurity, such as phosphorus, into a p-type silicon wafer. Silicon is a semiconductor with a band gap energy of 1.12 electron volts at room temperature. This is the gap between the valence band and the conduction band. Electrons can be raised into the conduction band by particles or photons with energies greater than 1.112 eV. The resulting electrons in the conduction band are free to conduct current. Photons with energies smaller than the band gap are not absorbed at all. Photovoltaic cells are essentially photodiodes. When sunlight strikes the surface of the cell, electrons are excited into the conduction bands and current flows. The power output depends on the surface area of the cell, the intensity of sunlight, and the quantum efficiency of the materials used to construct the cell. Additionally, thermal hybrids are being developed that convert sunlight directly into heat that can power a traditional steam turbine to generate electricity. As technology continues to develop, solar panels will become more cost competitive. Other important applications of instruments that rely on the photoelectric effect include spectrophotometers, UV visible, infrared emission fluorescence, atomic absorption, and Raman positron emission tomography, X-ray phototimers, chemiluminescent assays, DNA sequencers, calorimeters, oil well logging, laser components, LEDs, night vision, scintillation detectors, mass spectrometers, and electron microscopes.
So after all of that, Timmy, do you finally understand the photoelectric effect after all the examples that we provided?
And I really understand the photoelectric effect now. I'm gonna ace this test. Thanks. Where'd he go?
Actually, you know what? It's not working. Can you give me a ride home? And actually, like, some gas money would be great too. Do you have food?